Hi, today we are going to be looking at some vectors. The unit vector, the tangent vector, and the unit tangent vector, and something else that we call the normal vector. Now these are used quite a bit in physics, and they're all based around, imagine we have a particle moving along a path r of t that can be represented by this trace or path r of t right here. To find the vectors, we have the following formulas. To find the unit vector, we talked about this earlier this year. We actually have a video on that. You can watch it. It is totally amazing. Smash that like button. To get the unit vector, all we do is we take the vector itself and we'd of course divide by the magnitude, and that is going to give us a vector of length 1. Right here. Remember, that's what unit means. We have a vector of length 1. To find the tangent vector. Now, what is the tangent vector? Well, that's going to be the vector that touches our path in exactly one spot. Right here. So, that's our tangent vector. And we should remember from Calculus 1, in order to find a tangent line, we of course need the slope of the graph. In vectors, we call it the direction vector, but in either way, we are going to need a derivative. And that's what we're being told here. If we're given the vector, now there's my x component, my y component, my z component, they're all functions. To get the tangent vector, we really just take their derivatives, f prime, g prime, h prime. We saw this last year in Calc 2 when we worked with vectors, where we would take the vector x component and the y component independently from each other. And then to find the unit tangent vector, again, this is going to be the same vector above, but just 1 unit long. So so I have the length of 1. And what all this has to do is you're going to take the tangent vector and you're going to divide it by its magnitude. So that's going to be our tangent vector, but only 1 unit long. Next we have what's called the unit normal vector. Now we might remember normal means perpendicular. So what's going to happen here is we're going to find a vector normal to our unit vector. We use this a lot in physics, and here's what it's saying to do. It says take the derivative of our tangent vector. Well, remember, the derivative of my tangent vector is, my tangent vector is the derivative of my original vector. So if this gives me distance, this would be velocity. This is kind of like our acceleration. So now this is like our second derivative of our original vector. And you should recognize this from physics as being like an acceleration. So what does this give us? Well, in physics, this is saying that we are pointing inward, or we are perpendicular to the tangent vector right there. So what this is telling us that we are going to be perpendicular to r of t, and we're also going to be perpendicular to the tangent vector, which we identify this as t of t, the unit tangent vector as well. In physics, we would call this like our centripetal acceleration. Right there. And we kind of see that, like, remember, if you're spinning, or if you're going around a corner, right, your path is always tangent to the curve or the road, but your acceleration is being pointed inward, always perpendicular to your direction. So a lot of applications in physics. So let's take a look at a few examples in math. We want to find the unit tangent vectors for the following. And the first one, we got the vector 2t plus 1, t squared 4. Remember, this is a trace, right? In other words, it's a path on a surface. That's what a trace is. A path along a surface. And we want to find the unit tangent at t equals 1. So the first thing we're going to do, my rule says, I need to find its derivative. to get the unit tangent vector, I need the derivative. There's my unit tangent vector equation. So we're going to need v prime of t. And that's not bad to do. We just get 2t, 0. Derivative for 0. Next, we're going to need the magnitude of that. And that's just the square root of 4 plus, that becomes 4t squared. We don't worry about the 0, it just becomes 0. So our unit tangent vector would be the following: 2t0, and you can use your IJK form if you want to, over the square root of 4 plus 4t squared. Now we're not done. Remember, this is my derivative. This is like my derivative here. In other words, this does not find the slope. This is a slope. This is not the slope, excuse me. This is a slope finder. So that's my derivative. To get the slope, I have to plug in. In this case, t equals 1. If we plug in t equals 1, we're going to get 2, 0 over the square root of 8. And what this equation does, what this finds for us, this is the direction on r of t at t equals 1. So it's giving us the direction we are heading when t is 1 on that trace, or on that path. Very kind of neat to do. So let's take a look at number 2 right here. Same idea. This time we have sine t, natural log of t, and we want to find when t equals e. So we are going to take our derivative, and that becomes cosine t. The derivative of t is 1. Natural log, of course, is 1 over t. Finding the magnitude, and you can plug in e right away and get your magnitude that way, but the math is kind of fun for us. We get cosine squared of t plus 1 over t squared. And I'm going to go ahead and calculate the magnitude right now at e, and that's going to be on top cosine e, 1 over e. On the bottom, we get the square root of cosine squared e plus 1 over e squared. Leave it alone. Don't worry about simplifying this. That's pretty darn ugly right there. Yeah. All right, number 3 is an interesting one. We see this one quite a bit. What shape is this? Well, we should recognize that this is going to give me like x equals sine of t, y equals cosine of t. So this would be like saying x squared plus y squared is 1 if we convert from parametric to rectangular. So this is a circle on that xy plane. We should recognize that. But this is my z coordinates. Well, my z coordinates are also changing. So as I'm going around the circle on my plane, my flat surface, z is changing. So what does it do? It kind of raises it up. So this makes this a whole shape together makes a spiral or a helix. So it would look kind of like this. Oh. So we have our spiral. They want us to go ahead and find the tangent curve, the unit tangent. So we know we would need the derivative. So let's go ahead and calculate that. And that is, I'm going to use my Chevron form. I always like this form. Cosine t, negative sine of t, negative 3. Now, the negative, so t can be negative, so it can go up and down. That's okay. And remember, when we switch the sine and the cosine, it just changes our starting point and direction. We have an earlier video where you can take a look at that. Looking for the magnitude, we get the square root of cosine squared t plus sine squared t plus 9. This is why we like circles. Cosine squared plus sine squared is 1 plus 9. We get the square root of 10. So our unit tangent vector is going to be the following. Cosine t negative sine t negative 3 over the square root of 10. And there is our unit tangent vector. In other words, any point on the surface, right? So like if I pick a point here, it's coming out. Ready? There's t of t. It's following the path. Ready? I kind of think of like if I'm sitting on a staircase, a spiral staircase, and I go around, t of t gives me the direction I'm heading. I'm always on that path. This gives me this will find the direction on the path. Now, just for fun, we haven't done this yet, but let's go ahead and find the normal tangent, the unit normal. Sorry, not normal tangent. Vector. Well, to do this, my rule is that I need the derivative of my unit tangent. So I'm going to get my derivative. Now, the square root of 10 is a constant, so I can factor that 1 over root 10 out. And on the inside, we're going to get negative sine of t, negative cosine of t, 0. To get the magnitude, we got to divide by the magnitude. This is a little bit trickier. There's a lot of ways you can do this arithmetically. I'm going to do it the long way. We get the square root of, remember, if I were to distribute this root 10, it's going to go underneath every one of them. And if I square it, I get a 10 on bottom. So I'm only looking at the top, sine squared of t plus cosine squared of t, and the 0 just goes away. And what we're left with, that's just 1 over root 10. So to get our normal, unit normal, it's going to be t of t, so 1 over root 10, the derivative, the change in our unit tangent, negative sine t, negative cosine t, 0, divided by its magnitude, which is 1 over root 10. And yes, those cancel out. That's what's nice about circles. Those will always cancel. And what we're left with, negative sine of t, negative cosine of t, 0. Now remember, this is my second derivative. So this is the direction of my acceleration, which in this case right here, in our graph, in our spiral, will be pointing towards the center. Right there. All right. Hope you enjoyed part 1. Go to part 2. We'll take a look at a few more examples. Bye.